Part 2, Chapter 4, Calculating True Power AC Circuits. As mentioned before, the true power with the circuit is power actually used in the circuit of the power dimension and watt of the power associated with the total resistance in the circuit. To calculate the true power of the voltage current associated within the resistance must be used since the voltage drops across with the resistance equal to the resistance multiplied by the current of resistance. True power can be calculated by the formula. True power is equal to the amperage resistance squared times the resistance in ohms. Also, is the true power is measured in watts. The amp is the resistive current in the amps. Over the resistance amps, the true power is measured in watts. The IR stands the resistance and current amp the resistance in ohms. For example, the true power is shown in Figure 410. Show the resistance 60 ohms, reactance of the inductive reactance 30 ohms, inductive capacitive inductance, capacitive reactance 110 volts, 110 ohms, voltage 50 volts. So you start out with the reactance. A resultant of the 80 ohms impedance is equal to the ohm square root of ohm squared times the resultant impedance is equal to the square root of 60 ohms plus the square is the square root of 60 ohms squared plus the 80 ohms squared, which equals 10,000 ohms. So you get the impedance of 100 ohms. The amperage is equal to the voltage over the impedance. Amperage is equal to 500 volts over 100 ohms, which gives you 5 amps. Since the circuit current in the series circuit is true in all same power, the true power is equal to the amp resistance times squared times the resistance in ohms. True power of the 5 amps is equal to 5 amps squared times 60 ohms is 150 watts. Alright, calculating reactive power in the AC circuit. The reactive power term to do the sort of the reactive components of the circuit. The type of the power is measured in voltage, amperage, reactive, or abbreviated VAR. Reactive power is calculated by using the voltage current associated with the circuit in the reactance. So since the voltage reactance is equal to the resistance multiplied with the active current, reactive power can be calculated by the following. Reactive power is equal to the amps resonant is equal to is IX is the reactive current in amps times the total reactance in ohms. Another way to calculate the reactive power that to indicate into the inductive power and capacitive power about subtract the smaller from the larger. So you have inductive amp conductive time squared times reactance inductive times inductive amp inductive squared times inductive reactance minus inductive capacitation squared times capacitive reactance in amps capacitive squared times x or amps capacitive squared times capacitive reactance inductive minus inductive reactance in amps inductive reactance squared times inductive reactance, or reactive power is measured in volts. The amperage minus reactive. The capacitive and the current in amperes, and the capacitive IC is the capacitive and the current in amperes. XC is the capacitive and resistance in ohms. Reactives in ohms. IL is inductive currents in amps. XL is the inductive reactance in ohms. Either one of these formulas work. The formula will depend upon the values are given in the circuit. For example, the reactive power circuit figure 410 shows the inductive resistance in ohms is 30. The capacitive resistance in ohms is 110. The total reactance is 80 ohms. The amperage is 5 amps. Since the reactive power is 5A squared times 80 ohms is 200 volts. Volt amp is reactive. With a reactive power, it would be 2,000 volts reactive. You install this formula in capacitive current in amperes times the capacitive resistance in ohms minus the amperes squared times the inductive current in amperes times the inductive resistance in ohms. You get 275 voltage active amplitude. Voltage amps reactive. You add the voltage amps reactive. 275 minus 750. 200 voltage amps reactive. Alright, calculating apparent power in AC circuits. Apparent power is the power that appears for the source because of the circuit impedance into the impedance for the total opposition of the two. The AC apparent power of the power of the voltage is C. The apparent power of the combination of the true power and reactive power. Apparent power is not found by simply adding true power and reactive power. Just impedance is not found by adding resistance and reactance. To calculate apparent power, you must either have the following formulas. Apparent power is equal to impedance of the current in amps squared times the impedance in ohms, and apparently, or the square root of the true power squared times plus the reactive power squared. For given the impedance of 100 ohms, amps at 5, you have 2,500 volts amps apparent power. Apparent power. True power 150 watts, reactive power 2,000 volts, active 2 volts is. What's that again? I'm sorry I'm scooping through this, Alright, volt amps reactive. Okay. You have your apparent power is 200 volts active, true power 250 volts active. Alright, power factor. The power factor is the number represented with a decimal and percent of the represented with a portion of the apparent dissipated circuit. If familiar with the trigonometry, the easiest way to find the power is to find the cosine of the phase angle. The cosine of the phase angle is equal to the power factor. You need to use the trigonometry to find the power factor. Since the power is dissipated in a circuit as true power, apparent power is equal to apparent power times the power factor is equal to true power. Therefore, power factor is equal to true power over apparent power. True power, apparent power is known as usually the formula is shown. Given the one-step formula, another formula for power factor can be developed by substituting the equation for the true power and apparent power for the formula for the power factor. You get power factor is equal to the amperes and resistance, the amperage of resistance squared times the resistance over the amperes and impedance squared times the impedance. Since the current in series circuits are the same as all the parts in the circuit, amps and resistance and amps and impedance, their series and circuit power factor is equal to ohms over the impedance. For example, to compute the power factor with the series as shown in figure 410, any of the above methods are shown. True power would be 15 volts, 1500 volts. Apparent power would be 1500 volts apparent. Alright, so you get the power factor true parent over apparent power, 1500 watts over 25 volts apparent. You get power factor of 0.6. Another method is resistance 60 ohms, impedance 100 ohms equals 60 over 100 or 0.6 power factor. If you're familiar with trigonometry, you can either solve for the angle of the power factor. The refining table to specify appendix 5 and 16. Resistance 60 ohms. Reactance is 80. Tangent of reactance over ohms is resistance is 80 over 60, 1.33. And then you take your tangent of 1.33, you get the angle of 553.1, and you have therefore your power factor is cosine 0.6. Note, as stated earlier in the power factor, can be expressed in decimal percentage. In this example, the decimal power is 0.6, should be expressed as 60%. Alright, the power factor correction. Apparent power in the AC circuits has been described as the power for the seats. As far as the source is concerned, apparent power that must be provided with the circuit. You must also know the true power with the power actually used in the circuit. The difference for the apparent power and true power is wasted because of the reality. Only true power is consumed. The ideal situation would be the apparent power of the true powers to be equal. If this were the case, then power factor would be 1 unity or 100%. The two ways in which this condition can exist is 1, if the circuit is purely resistive, or 2, the circuit appears purely resistive to the source. To make a circuit appear purely resistive, there must be no reactance. To have no reactance in the circuit, the inductive reactance and the capacitive reactance must be equal. Remember that the reactance is equal to the Inductive reactance over the minus the capacitive capacitive reactance. Inductive reactance equals the capacitive reactance is if the reactance is equal to 0. Alright, the expression correcting the power factor refers to reducing the reactance in a circuit. The ideal situation have the no reactance in the circuit with the accomplished for the adding of the capacitive reactant if the inductive and inductive reactance to a circuit with a capacitive. For example, shown in figure 410, the total resistance to 80 ohms capacitive with a power factor of 60%. The 80 ohms and inductive reactance would be added to the circuit. Adding another inductor, the circuit would have the total resistance of 0 ohms and a power factor of 1 or 100%. The apparent and true power of the circuit would then be equal. Alright, series and RL resistor inductor current capacitive circuits. Principle of the formulas have been presented with the chapter for the U of all circuits. Examples given in the series circuit. The section of the chapter will not present any material, will be an example using all the principles presented so far. You should follow each of the example of the problem step by step to see how each formula depends upon the information determined in the earlier steps. When an example for the square root, you must practice the square root table locating the values given. The series of the resistant inductive capacitive circuit is shown for figure 411 as the inductive capacitive reactance, impedance, and total amperes, total true power, reactive power, and apparent power and power factor. The value solved will round it off the nearest whole number. For these, first solve the capacitive inductance and the inductive reactance and the capacitive reactance. Alright, you got 60 hertz with a inductance of 27 millihenries, or a capacitive of 380 US farads. You get the capacitive inductance would be then 10 ohms. The capacitive capacitive reactance would be 7 ohms. Figure 411 example, the RLC circuit. You notice that the voltage and frequency is at 60, the resistor is at 4 ohms, the L is at 27 millihenries, and the capacitor is at 38 microfarads. So you have the 10 minus 7 to get the reactance or inductive 3 ohms. The value of the reactance is 3 ohms over 4 ohms, so you get the reactance to solve for impedance. The reactance is 3 ohms. The resistance is 4 ohms. The impedance is equal to 3 squared. 3 squared plus 4 squared equal 25, or the impedance is 5 ohms. You can value the Z can be used to solve the total Z. The impedance of 5 ohms, the voltage 110. You get 110 volts over 5 ohms, which gives you 22 amps. Since the current is equal to all parts of the series circuit, the value of the amps total can be used to solve the various values of the power of the power. Amps total 22 amps. The amp is total 22 amps. Resistance 4 ohms. Reactance 3 ohms. Impedance 5 ohms. True power would be the amp squared. Total amp squared 22 times the resistance 4 ohms would give you the 1,936 amps. If a true out 1,936 watts. Sorry. Reactive power would be the amps. The amps reactance are 22 amps plus squared times 3. The reactance 3 ohms, 152 volts active active reactive. Apparent amps and impedance squared times the impedance is give you a voltage amp 2420 VAs. Power factor can be found by using the apparent power, the true power of the resistance, and the impedance of the mathematics. Example is easier the impedance and resistance. Resistance is 4 ohms, impedance is 5, so you get 4 over 5, which gives you 80% power factor. Alright, parallel, resistive, inductive, capacitive circuits. When dealing with a parallel AC circuit, you find that the concepts presented in the chapter series of AC circuits still apply. One of the major differences between series circuits and parallel circuits is that must be considered the difference if the current is the same in all parts series circuit, whereas the voltage is the same across all branches in the parallel circuits. Because of the difference of the total impedance of the parallel circuit must be computed as the basis of the current in the circuit. Remember, you should remember that the resistance, inductive, capacitive circuit follow the three formulas or RLC. Capacitive is equal to the capacitive inductance minus the capacitive inductive reactance minus the inductance capacitive equals and reactance equals equals capacitive reactance minus inductive reactance. Impedance equals the square root of the amperes, the total amount of resistance in the amps squared to minus the reactance plus the reactance squared, or power factor is equal to ohms over impedance. The parallel circuit, you must follow the following formula. Alright, the amperage, the total amperage reactance is equal to the amperage inductance minus the amperage capacitive or inductive reactance is equal to inductive capacitive minus the inductive and the amps inductive. The amps impedance is the square root of amps resistor squared plus the amps resistance squared, or power factor is equal to amps resistance over amps impedance. The impedance parallel circuit is found by the formula Z amp impedance is equal to voltage over the amps impedance. Note that no value of E is given in the circuit. In the circuit value, E can be assumed to find the value of the amps inductive and amps and capacitive and amps and reactance, amps and resistance, and amps impedance. Same voltage then is used to define the impedance. For example, the Z is given as shown in figure 412. The voltage is 300. The resistance is 100 ohms. The inductive reactance is 50 ohms. The inductive capacitive reactance is 150 ohms. So you have 300 volts over 100 ohms will give you 3 amps of the amps resistance. The amps inductive is equal to voltage over the reactance amps, which is 300 volts over 50 amps, 6 amps. Inductive capacitive is volts over the inductive capacity, 350 amps over 100 amps is 2 amps. So then you'd have this one would be 2 amps, this one would be 6 amps, and then the first circuit, the resistor, would also be 3 amps. Now take your to find the amps and the reactance, you take the 6 amps minus the 2 amps, get 4 amps inductive. The impedance is equal to the amps resistance squared, 3 amps plus the amps reactive squared, reactance squared, 3 amps squared plus 4x squared, 25 amps. Amps impedance is 5 amps. Or the impedance is equal to voltage over the amps impedance is 300 volts over 500 amps, or 300 volts over 5 amps gives you 60 ohms. The value of the E is not given that you are asked to solve the G. Any of the following E could be assumed in the example of the question. 50 value of 50 volts for E, with the solution would be, alright, you'd have 100 amps over the inductive reactance, so 50 ohms, and inductive capacity of 150 equals E. The voltage would be 50 volts assumed. First, solve the value of the amps resistance over voltage over the resistance. It would be 50 volts over 100 ohms, which would give you 0.5 amps. Inductive would be voltage over the inductive reactance, 50 volts over 50 ohms, 1 amp. Inductive amps capacitive would be voltage over the capacitive reactance, or 50 volts over 150 ohms, or 0.33 amps. Alright, taking 1 amp and 33.3 amps, you get 67.8 inductive amps, or 0.5 amps squared plus 67 amps squared equals 0.689, or square root of that is 836 amps. Alright, the impedance is equal to volts over the impedance amps, which would be 50 volts over 836 amps, would be voltage is 60 ohms rounded off. When the voltage is given, you can use the value of the amps, resistance amps, reactance, and amps impedance to calculate the true power, reactive power, and apparent power with a power factor circuit shown in Figure 412, with the calculations would be as follows. Given the resistance is 100 ohms and the amp resistance is 3 ohms, the true power of the amps resistance is 3 amps squared by 75 amps. For 75 ohms, 900 true power watts. To find the reactive power, first find the reactance X. 300 volts. The inductive reactance is 4 amps. So the reactance of 300 volts over the 4 amps would be 75 ohms inductive. So the reactive power of the 4 amps squared times the 75 ohms reactance equals 24 volts apparent reactive. Given that to find apparent power, given that the impedance is 60 amps and the impedance, the amps impedance is 5 amps, the amps impedance squared times the impedance is 60 amps, volts apparent. I believe A is apparent. We'll find that out as soon as we get to the end. Power factor in the parallel circuit is found with the following methods. Given the true power is 900 watts, the apparent power is 150 volts VAs, or the power factor would be 900 watts over 150 A's, or 0.6. Given the amps resistance is 3 amps and the amps impedance is 5 amps, you get 3 amps over 5 amps, which gives you a power factor of 0.6. And we'll go back and we'll look at the alright, volt amps. It is A is amps, and it's called VAR, stands for volts amps reactive. And that completes chapter 4.